WOPM in Sydney. Sorry I couldn't make it this year due to some paperwork issues, but hopefully I can present this talk in a pre-recorded manner in a way that you can get the full gist of what I was trying to say. And I guess let's get right down to it. This talk is titled Miniaturizing MEG, the Future of Epileptic Signal Localization. And I just kind of want to emphasize, although I do say epileptic signal localization, what I really want to kind of get across in this talk is the really sky-high potential that optically pumped magnetometers have in the field of neuroimaging in general, whether it be in clinical population or in research population. I think that really kind of developing sensors in that direction could provide some great medical breakthroughs, and in the sense of getting this advanced imaging technology of magnetoencephalography into the hands of doctors and to the patients that need it. So I guess let's get right down to it. On the left here is our cryo or squid magnetometer MSR, and as well as our squid MEG system. And on the left here, you can see there's actually quite a large room, and you can see here at the floor, it actually has to be isolated from the rest of the hospital, which meant digging up the foundation of the hospital and actually combining two separate rooms that were separated and knocking down the wall. And then a place like UT Southwestern, where space is a premium. This was a very costly endeavor. So the infrastructure costs for actually putting in a squid MEG system can be quite high. And you can see here on the right, we have our large tower that's for the liquid helium required to supercool our squid systems, our chair, and then the helmet that the person is raised into. And this is not a very mobile system, as in not at all. So the big thing with MEG is the localization efficiency and the accuracy compared to something like EEG for neural imaging, like I said, is quite high, but the portability is quite low, and it requires a extensive research institution to have the funds to get one of these systems, and also for the maintenance, they are quite high. And in this diagram, I just want to hit the point home a bit more, that these are complex systems that require a constant supply of liquid helium to supercool the sensors, and a system like this could have, in our particular system, we have 204 radiometers and 102 magnetometers. And these are very complicated systems, and you can see here, the person's head is there. We raise them up into the helmet, like I showed before in the chair, and then the person's head is here, and then the sensors do their thing. And by using this, we can get very high signal localization accuracy if we have the participant's T1 MRI, or even using a template brain. But this comes at a very high cost. We have a recycler on our system, but there are a lot of people that don't. Requires a constant supply of liquid helium, and this tower is quite sensitive. You cannot move it. And this is where our optically pumped magnetometers come in. So you can see here, just a schematic of a usual OPM kind of setup inside the device. And you can see here, no liquid helium. And these little rectangles are quite small. As you can see here on the right, a Q-spin OPM magnetometry system that they can fit into a 3D printed helmet and then moved as needed around the head. And also these systems can be removed and taken where they're needed. And this helmet itself is free floating, so unlike the actual fixed helmet system in chair, the person's head can move while these sensors are in place, much like an EEG. And this is a huge advantage, especially when you're dealing with pediatric patients and people that have moving problems. Getting them into the squid magnetometer can be quite an issue. Both the OPM sensor, if they can put on a helmet, they can use the device. which is a big plus. You can see here on the left, there I am. Our normal preparation for this is we put a swim cap on the participant, and we put these little neon green patches on the anatomical positions and on the positions of the actual OPMs that we have in the helmet. And we use these later to actually get our positions relative to the person's anatomical positions. And on the right is the final setup. So once they have the helmet, I should say, on. And here is a slightly different configuration than on the left, but just so I can show them all on the actual picture. But we have a total of 10 sensors currently, and these are arranged in a circle around the head. But you can adjust them as needed. So even with a small number of sensors, if you know the area of activation for your experiment, you can position them all around the area that you need. And in this way, as I said before, our current SQUID MEG system has 306 sensors. These OPM magnetometers can also be, although they are on a per sensor basis quite expensive. Using a small amount, 10 in our case, you can get very good quality data if you use the system in an intelligent manner. And if you adapt it to your experiments, then a small number of sensors can go a long way for a lab. And here's our final setup. The beanbag is actually an idea of one of our clinical MEG technicians. There is no magnetic, any magnetic metal or anything like that in our beanbag chair. But whenever we're doing something like an epilepsy scan, looking for April spikes, having something that a pediatric or just a person with movement issues can get comfortable actually in our MSR is something that is quite advantageous. And like I said before, our helmet here, the person is completely free to move their head. And once they're on the beanbag, it's a very comfortable environment. And this MSR is small enough that it is portable in the sense that it can be broken down and then rebuilt elsewhere, unlike the SQUID MEG system, which we had to dig up the foundation of the hospital. So once again, huge advantages of using the OPM MEG. And in this MSR, we can actually project onto the opposing wall from outside. We have an intercom and camera system, and we can integrate everything that we can in our SQUID MEG in our little portable MSR with the OPMs. So lots of advantages here. And this is something that you could put in an epilepsy monitoring unit, in a small clinic, anything like that could be shared between different sites that need it. So these are all huge advantages, and this is the point I'm trying to get home, is that OPM MEG can provide something that is normally only for the highest kind of research institutions and hospitals in a package that is accessible to the rest of the world, in the sense that for a small startup cost, 10 sensors, MSR, something like that, you can get this highly localized data that you would only get from a SQUID MEG system in a package that is affordable or accessible. And with a small number of sensors, you can get a lot of data, which I'm going to show. But in the general methods, we have a calibration process where the person is in the MSR, calibrate the sensors with their wearing helmet in order to get their baseline noise and the noise of the environment out of the way. And we acquire our raw data here, and then using the points before that we took of the OPMs in the anatomical positions, we can then project onto their T1 MRI or a template brain if T1 isn't available. We can clean our data just as we can with our SQUID MEG system by doing band passing, artifact removal, all the same things. And we project that data onto the positions that we know beforehand to get an image like this, which is created in Brainstorm But you can use your neuroimaging package of choice, whether it be M&E, Brainstorm, Field Trip, what have you. You can get these positions, get the data, and with a lot of hard work, feed it in the same way that you can with the SquidMag system. So part of what I'm working on is making this process a little easier in the future. And so the overall process from start to finish would be putting the helmet on the participant, doing the calibration, getting the raw data, and then in the post-processing period, taking those positions that we did before, projecting the data, performing a power spectrum density, which is like Fourier transform analysis, in order to get the power in different frequency bands, which we're concerned with in the field of neuroimaging. And then after we get the group average data, we can then take the participants and perform a statistical non-parametric t-test in this case, or any kind of statistical test versus a baseline or a different group of participants, and get our final statistically significant image. And this is a normal thing that we do for other kind of sensors or modalities, but this is our typical pipeline for the OPM MEG. And for this particular experimental protocol for the data I submitted today, we would have our baseline period, motor, visual, and then a language test. And this is kind of mirroring what we have in the clinical SquidMag scan, but these are all 3 minutes. So it's a kind of hyper-condensed version, not necessarily hyper-condensed, but a condensed, more streamlined version of what we do in the clinical MEG scan, which takes a total of 12 to 15 minutes. Maybe a little more with calibration, and they are all compared to the baseline for significance, and we have a total of 8 subjects now for this particular experiment, but we are doing more experiments now, or I should say more protocols. And so what this entails is we have them tap their right hand finger tapping, I should say performing a right hand finger tapping experiment where they tap their right index finger. And that should activate an area here. This is a very well-known experiment. Your right hand activates part of your left hemisphere of your motor cortex. Have a visual stimulus projection. So like I said before, this projection, it comes through a kind of pipe on the side, and we can project into the system without causing any interference onto the wall on the opposite side. And project an alternating checkerboard pattern, which would look something like that. And this alternating checkerboard stimulates the occipital area of the brain that has to do with your visual processing. And the final language task, we once again use the projector, project a noun onto the wall, and then they have to think of a verb that goes along with it. So, for instance, if I were to project ball on there, then you can think of throw or swing or anything like that. In order to stimulate Broca's-Wernicke's area, these kind of areas that are important for language processing in a way that is stimulating those areas, and then we can see it on the scan. And so the results from these particular on our 8 epileptic patients, you can see these are kind of our baselines to make sure that the system is working and comparable to other modalities. On the left here, you can see the beta frequency band. This is our expected on the right from a previous paper. You can see that they are quite closely matching. This motor area is exactly what is lighting up on our OPM MEG, or for these statistically significant areas from the OPM MEG scan. On the right is our expected for our visual task, which is that checkerboard. It's predicted here. Then you can see that the occipital area is lit up, and then our statistically significant area here is in the occipital area in the alpha band, which is what we would expect. And just to add to this, you can see it is actually quite weak significance. It is still significant, but the t-values are much lower. But this is most likely due to the sensors being in that circular pattern, as I showed in one of the first few slides. In order for us to get the whole brain, we didn't want to bias towards any particular area because an epileptic spike can come from anywhere. So we put them in a ring around the head, and the occipital area is the area that is farthest from those sensors on the side. So that probably explains why we see a weaker signal, but if they were sensors closer to the back, we would expect the significance to be higher. And finally, for the language task, this is the one that we're actually most excited about. On the right here is an MRI representation of Broca-Wernicke's area, the areas that should light up. Now on the left here, we can see those two areas are very strongly lighting up and very significant in the alpha band, which is what we would expect to see. And this is very kind of confirming, or very affirmative, that these OPM systems, even if you only have a few, 5 on each side or 10 in total, that you can get some very appreciative, or I should say very meaningful data out of a very small number of sensors. And here's our, we're also concerned that maybe some correlation or or connectivity might be lost with the system compared to SquidMeg. You can see here we use a software package known as eConnectome to actually generate 3D images of this connectivity, and then the language tasks. The two areas we expect to be connected are connected very significantly. So this is all good, but and this is more of a research-based scan or something that we would do. But what about the actual clinical scan? These are epileptic patients. If they have an ankle spike, how does that look compared to the SquidMeg? So on the right here is our SquidMeg. These are dipoles that are localized by our epileptologists. They're all localized to this particular area that you can see here. And then on the left is our OPM of the same person. They're taken immediately after their SquidMeg into the OPM MEG next door. We run the highly condensed protocol. And you can see that the same area is in fact lighting up in the DSPM analysis on the left. So the ankle spike is localizing to the same area, which is very affirmative. And here you can see we actually took the average for all 8. We did a SNR analysis to get the signal to noise of both systems to make sure that, or just rather to see how the SNR might differ between a SquidMeg system versus our OPM MEG. And when using the same number of sensors, the SNR is appreciably the same. At least in these subset of 8 participants. We need to, of course, collect more in order to have a definitive kind of say on that. But from these 8 subjects, the SNR is fairly comparable to our SquidMeg system. So these are all very good kind of preliminary results saying that yes, SquidMeg can be used in the same manner that or I should say OPM MEGs can be used in the same manner that a SquidMeg system can be used. So this is all very good affirming data. So where can we take this project? You know, expand it into more, we're trying to put more epilepsy data in on other patient populations to make it a little bit easier to use in our various neuroimaging packages like Brainstorm, and also to develop the system further to make it easier for the average person or average clinical tech to be able to easily use these OPM MEGs to perform these neuroimaging scans. And so currently our ideal patients are older teenagers, super spikers with frequent large spikes, and then, you know, patients that are willing to give up 20 to 30 minutes of their time after an already quite harrowing scan when they're very sleep deprived. So these are our ideal patients we kind of look for. They're ideal in our opinion for these OPM MEG scans. And if you have any questions, please feel free to contact me at this email here, Tyrell Pruitt at Southwestern.edu. And I hope I got across the high potential for OPM MEGs and in the field of neuroimaging, and how hopefully in the future they can get easier to use, and you know, with a bit more, a few more studies, I should say, hopefully they can become a bit more widespread, and we can get them into clinics and EMUs. So if you have any questions, feel free to contact me. Thank you very much.